Good day, I'm Norman Wahlberger. In today's video, we're going to carry on thinking about the isometry groups of the projective line. And I want to expand the discussion today by changing the base of our pizza, by moving from the rational number underlying number system to a finite field, in particular to the very simple finite field with only 3 elements, and then we'll have another look at the finite field with 5 elements, the same story. So this still gives a very rich Euclidean geometry, and most of the aspects of Euclidean geometry that we're familiar with, when stated in the correct general way, have a manifestation in this geometry over a finite field setting. But surprisingly, there are also some new developments. Okay? In particular, there's this phenomenon of null lines, or for us, null points, which we have not yet seen in the rational situation, but which becomes rather important for some finite fields. So these are familiar enough to physicists, physicists who are working with Einstein's theory of special relativity. For them, the relativistic analogs of these things are playing a very important role and correspond, in fact, to the propagation of light and photons. But in fact, it turns out that these null lines or null points are really an intrinsic aspect to Euclidean geometry as well, once we start to think broadly enough. So we're going to be talking about some algebraic structure called group structure, which arises from looking at the isometries of this projective line with the Euclidean framework on it. We're going to be interested in laying out this group structure very explicitly. And to do that rather efficiently, I'd like to introduce a little bit of additional notation that simplifies a little bit discussion of projective points and rotations and reflections. Here's our familiar situation, projective points. So this one is the 1 to 1, this one is a 1 to 2, this was 1 to 0. What we're going to do is we're going to introduce a bit of new notation. So when we have a projective 1 point like this, we can think about the line x equals 1 in the ambient two-dimensional space. And that gives us kind of a reference or a viewing line. And most every projective 1 point will meet this green line in a single point, which has x coordinate 1. That allows us to specify such a projective 1 point by only specifying what the y-coordinate is of that particular point that it meets this green line on. So for example, this line here can be written as the point 1 to 2. It can also be written as 2 to 4 or 3 to 6. But if we normalize so that that first coordinate is 1, then the second coordinate is unique, and we can therefore then represent this projective point more efficiently by just calling it a sub 2. Similarly, this line, or this projective 1 point, can now be referred to as a sub 1. This one as a sub 0. This one as a sub minus 1. And every projective 1 point can be expressed this way, with the sole exception of the vertical one, the one whose name is 0 to 1. We cannot normalize that so that its first coefficient has 1. And so, in keeping with our thinking in earlier videos, when we were talking about the projective line and adding a point at infinity, we actually had the viewing line horizontal in that case. Here we're having a vertical viewing line, which is more appropriate for what we're doing here. And there we refer to this thing as a point at infinity, and so in keeping with that, we'll call this projective 1 point a sub infinity. And then in keeping with that, we'll shorten our notation for rotations and reflections, so that a rotation of the form 1 to L will be shortened to just rho sub L, while rho sub 0 to 1 will be called rho sub infinity. Similarly with reflections, sigma 1 to L will be called sigma L, and sigma 0, 1 will be called sigma infinity. Alright, so here are the two fundamental formulas that define our projective rotation and our projective reflection. How would we translate these into our new, more efficient notation? Well, if we call this thing A sub L and call this thing rho sub K, means we're basically assuming this is of the form 1 to L and this is of the form 1 to K. Well, this is 1 to L and this is 1 to K, then this is going to be 1 minus K times L, and this is going to be K plus L. And then when we renormalize this so that the first coefficient is 1, we have to divide by this term, giving the expression K plus L over 1 minus K times L. So please check that that actually works, and that similarly this formula for the projective reflection is transformed in this sort of more efficient setting in the following way, that if you take a projective point L and apply sigma k, then you get A sub k minus L over 1 plus KL. There's a bit of symmetry here. The plus sign here changes to a minus sign, while the minus sign here changes to a plus sign. These are going to be useful formulas for us. They efficiently tell us how the rotations and the reflections act on our projective 1 points, written more efficiently in the form A sub L. To clarify those more efficient formulas, here are some special cases or perhaps additional formulas that help us in recording what the effect of rotations and reflections are on various things. All right, so I'll leave you to check these various formulas. All right, now I'd like to turn to the main object in this video, which is to try to generalize our projective one-dimensional geometry to the case where the underlying number system is a finite field. And the finite field that we're going to start with is the arguably simplest one, f sub 3, which is determined by a single rule that 3 equals 0. And otherwise it's pretty well like rational number arithmetic. So for example, in f3, if we wanted to add 14 over 17 plus 25 over 19, we would replace the 14 with 2, because we can throw away that multiple of 3, which is 12. We replace the 17 with 2, because we can get rid of the multiple of 3, which is 15. Similarly, 25 is replaced with 1, throw away 24, and 19 is replaced with 1, throw away 18. And then we do ordinary arithmetic, that's 1 plus 1 for a total of 2. Well, similarly, for example, here 10 over 11 is minus 49 over 7. 10 is the same as 1, 11 is the same as 2, 49 is the same as 1, 7 is also the same as 1, so we have 1/2 minus 1, which is minus 1/2. And then there's this trick of converting that into an actual integer by, in this case, multiplying top and bottom by 2. The 2 squared on the bottom becomes 4, which is the same as 1, so we basically just get minus 2, which if we like to is the same as 1, because we can add 3. Okay, so by this method of adding multiples of 3 or subtracting multiples of 3 and getting rid of denominators by this kind of trick, we can take any number in our system and convert it to one of these three, to either 0, 1, or 2. Or alternatively, one of the numbers minus 1, 0, 1. This is going to be a little bit more convenient for us, for our particular application. This is usually a little bit more familiar. These, in fact, are the 3 most important numbers when we're doing arithmetic. All right, so the field F3 consists of exactly the 3 most important numbers. And then here are 2 little tables that record addition and multiplication in this domain with the numbers minus 1, 0, and 1. So for example, if we wanted to add 1 plus 1, here's 1, there's 1. 1 plus 1 is minus 1. Usually 1 plus 1 is 2, but if we are allowed to subtract 3, then that's the same as minus 1. And multiplication, minus 1 times minus 1 is 1. Minus 1 times 1 is minus 1. 0 times anything is 0. 1 times anything is the original thing. So all of the arithmetic is contained in these two tables. Just a finite amount of arithmetic. All right, and now let's do some geometry. We'll talk about the projective line P1 over this finite field with three elements. Here are the projective 1 points. 1 to -1, 1 to 0, 1 to 1, and 0 to 1, which we're going to denote by a sub -1, a sub 0, a sub 1, and this one, a sub infinity. Every other projective 1 point is the same as one of these. So for example, 2 to 2 is the same as 1 to 1, because it's just a multiple of that. 2 to 1, for example, is the same as 4 to 2, which is the same as 1 to 2, which is the same as 1 to -1. Okay, and then we have our formula for projective quadrances, and it's the same formula as before. So for example, if we want the quadrants between a sub -1 and a sub 0, that's the quadrants between 1 to -1 and 1 to 0. The formula is 1 times 0 minus 1 times -1, all squared, over the product 1 squared plus -1 squared times 1 squared plus 0 squared. This turns out to be a half, which is also equal to -1, but I'm going to keep the half here because it connects a little bit with our familiar thinking. So we could say that the half is the same as -1, but we'll leave it as a half. And here then is a table of the quadrances between these various 4 points and themselves. The quadrants between any point in itself is 0. The quadrants between a -1 and a sub 0 is a half, as is the quadrants between a -1 and a infinity, while a -1 and a sub 1 are perpendicular because their quadrants is 1. And when I say quadrants here, I'm talking about projective quadrants everywhere. Let's have a look at a visual representation. How can we visualize what's going on? Well, we can take a grid, which is basically the affine 2 space formed over the field f sub 3, which has 3 times 3, or 9 points. There they are, with x-coordinates going from -1 through to 0 up to 1, and y-coordinates -1, 0 to 1. And then the actual projective points are lines through the origin in this case. And there's a sub 0, there's a sub 1, there's a sub -1, and there's a sub infinity. So for example, a sub 0, what we're calling a sub 0, can be thought of as the point 1, 0, or the point -1, 0. Those are both representations of a sub 0. A sub 1 represented by 1 to 1 or -1 to -1. A sub infinity represented by 0 to 1 or 0 to -1, etc. And if we think about these things as actually short little lines, each sort of line only containing essentially 3 points, then we can draw right angles representing perpendicularity much the same way as we do in the ordinary rational plane. And we can denote a projective quadrants between that line and that line by a little line and a half there, representing the fact that the quadrants between a 0 and a -1 is equal to a half. So these two 1 points are perpendicular. These are also perpendicular. And every other non-zero quadrants is a half. So now let's have a look at the rotations and reflections in this situation. Here is our geometry again, our visualization of it. And now we're talking about the rotations rho sub k and the reflections sigma sub k. And the formulas for the rotations are just the same as they are in the Euclidean case. And now you can check, using the formulas, that these three tables, together with this one here, explains or covers all the possible ways that we can multiply a point by a rotation. This is the simplest because this rotation rho sub 0 always acts as the identity. Any point a sub l times rho sub 0 is equal to a sub l. Geometrically, if we think of this as meaning the rotation acts on this point to give us this point, this is telling us that rho sub 0 is the identity transformation which takes any point and leaves it fixed. But remember, that was only one of several possible interpretations of what this formula might mean. But nevertheless, we'll stick with that interpretation because it's physically interesting for us and it's one that we're familiar with. So here, for example, this is telling us that rho sub 1 is basically a rotation. It sends a0 to a1, sends a1 to a infinity, it sends a infinity to a sub minus 1, and it sends a sub minus 1 to a sub 0. It's doing just what we expect a rotation by 45 degrees or an eighth of a turn to look like. Rho sub minus 1, that takes this to this, this to this, this to this, and this to this. It's the opposite direction to rho sub 1. And rho sub infinity takes a sub 0 to a sub infinity and takes a sub infinity to a sub 0. Takes this to this and this to this. And similarly, it takes this one to this one and this one to this one. So this one fixes all four. These two move every one to a different one. And this one here interchanges two in pairs. Okay, correspondingly, there are formulas for the four reflections. So what is the effect of sigma 0? Well, it sends a0 to a0, sends a1 to a minus 1, it sends a minus 1 back to a1, and it sends a infinity to a infinity. Geometrically, you can think about it as like reflection in this line, which sends this line to itself, which sends this line to itself, and interchanges these two lines. So I've written this a little bit more efficiently this way, so that sigma 0 sends a0 to itself and back again, a infinity to itself and back again, and interchanges a1 and a minus 1. Sigma 1, on the other hand, interchanges a0 and a1, and interchanges a infinity and a minus 1. You can think about it as reflection in a fictitious line about here, or also a reflection in a fictitious line about here. Here is sigma minus 1. What it does, it interchanges a0 and a minus 1 and a1 and a infinity. And sigma infinity is a little bit more like this one. It fixes a1, fixes a minus 1, and interchanges a0 and a infinity. Alright, so these, encoding a lot of formulas, all basic consequences of the basic definitions of reflections and rotations, and you can check these. And you might like to play around with composing them, and what happens if we do this reflection and this rotation and so on. Because now I'm going to put all of that together, how the whole structure of all 8 of these isometries looks like when we think about their group structure. Alright, and now here we come to the group structure of these 8 isometries, which is a very interesting and important mathematical object, an algebraic structure which is very simple, or relatively simple, still not that simple, but plays an interesting role in group theory, very important role in group theory, and also in linear algebra, as I discuss in my Wildland Alge series on linear algebra. Okay, so what does this mean? Well, here we have the 8 isometries, the 4 rotations, and the 4 reflections. And here similarly 4 rotations and 4 reflections. And these entries signify the product of these various things. So this rho sub 1 means that if we take rho sub infinity and multiply it by rho sub minus 1, we get rho sub 1. And what that means is that it's basically rho infinity times rho minus 1 equals rho sub 1. So if we act by multiplying by this one, and then we act by multiplying by that one, that composition is the same thing as simply multiplying by rho sub 1. Okay, there's lots of interesting things to do here. First of all, one should check this table, make sure that it actually works. That can be made simpler if you know a little bit of linear algebra. A little bit of 2x2 matrices helps us here. So here are the corresponding 2x2 matrices, for those of you who know some linear algebra, that correspond to these isometries. And there's of course some interesting things about this table, because this is actually a group multiplication table. It satisfies the crucial properties that it's associative. And you can check this associativity by taking any 3 elements, say rho infinity, rho sub minus 1, and say sigma 1, and multiplying them in that order in 2 different ways. So we can take rho infinity times rho sub minus 1, that's this one here, and then if we multiply this by, what do we say, sigma 1, that would be rho 1 times sigma 1. The result would be sigma 0. If we did it the other way around, if we took rho infinity times rho sub minus 1 times sigma 1, we should calculate rho sub minus 1 times sigma 1, which we do by going here and here. We get sigma infinity. So the effect of that is rho infinity times sigma infinity over here, which is sigma 0. So basic associativity holds for this diagram. And you can check various instances of that. Very useful thing to do. We can know that each element appears in every row and column exactly once. In particular, the identity element, rho sub 0, occurs in each row exactly once, and occurs in each column exactly once. In fact, every element occurs exactly once in each row and column. So that basically covers both the identity and the inverse properties of a group all at once. This group multiplication table has a very special role in group theory. It's one of the 2 non-commutative groups of order 8. There's another one called the quaternion group, which also plays a very important role. Okay, so it's a lovely example, very explicit, very concrete. There's no ambiguity whatsoever. But of course, we have to check that things are really correct. So please have a little bit of a check and see if you really agree with this table, and you can play around with a little bit of group theory. Now we're going to look at the same situation, but over F5, the finite field with 5 elements. We can think of those 5 elements as being minus 2, minus 1, 0, 1, and 2. And so here is the affine 2 plane formed from the field with 5 elements, with 5 times 5 elements, x going from minus 2 to 2, and y going from minus 2 to 2. Projectively, we're still thinking about lines through the origin in this situation. And what does that mean? Well, we can take just proportions. That's really what it means. Each one of these things is a proportion and represents a line through the origin. So for example, this one here, 1 to minus 1, is that point there. And that line, that proportion, is the same as the proportion 2 to minus 2 if we multiply both of them by 2. It's the same as minus 1 to 1, what we get when we multiply both of them by minus 1. It's the same as minus 2 to 2. So each of these 4 are just another name for this one point. Here is a sub 0, which is this one. Here's a sub 1, which is this one. Here is a sub minus 1, the one we just talked about. Here's A infinity, this one. But there's also two lines here, A sub minus 2 and A sub 2, which are a little bit different. And you can see that geometrically they look different. So A sub 2 consists of this one, as well as this one and this one visually. A sub minus 2 is this one, this one, this one, and this one. It really is just proportion. So if we look at A sub minus 2, which is 1 to minus 2, that's that point there. If we multiply this by 2, we get 2 to minus 4, which is the same as 2 to 1, which is this point here. So although it doesn't look like it geometrically, this point in the affine 2 plane is really twice this point in the field F5. So this is actually a multiple of this one, just as this is a multiple of this. Just that visually it looks a little bit different. But that's not what's really different about these two 1 points. The difficulty or difference between them is that these are what we might call null points. And what makes them null points is that the sum of the squares of their entries is 0. 1 squared plus minus 2 squared is 5, which is 0 in F5. And similarly, 1 squared plus 2 squared is 5, which is 0 in F5. This is a new kind of phenomena that we don't get in the rational numbers and that we haven't seen in F3 either. One of the consequences of this is that when we are talking about projective quadrances between these 1 points, these two are going to behave differently. Because in the formula for the projective quadrants, this sum of squares appears in the denominator. And if you have 0 in the denominator, it means that things basically don't work arithmetically. So what we're seeing is that the quadrants, or the projective quadrants, between these points and any other point is undefined because there's a 0 in the denominator. Our formula gives us zeros in the denominator. Notice that otherwise, if we just restrict ourselves to these 4 points which are not null, that the pattern of projective quadrants looks a lot like it did in the F3 case. In fact, it looks exactly the same. A sub minus 1 is perpendicular to A sub 1. A sub 0 is perpendicular to A sub infinity. And all the other projective quadrants are a half between two different fellows. And the quadrants between any 1 point in itself is, of course, 0. All right, so this is a very interesting phenomena that we're only seeing here for the first time when we've extended our Euclidean geometry to the finite setting and we've gone to the field with 5 elements. We didn't see it in the field with 3 elements, but with 5 elements we're seeing something that we haven't seen before, the idea that we have a null point. Our one-dimensional geometry has some special points which are in some sense singular. They are special. The definition of the metrical structure is more problematic for them. We have to admit that the formulas that we write down actually don't work for those particular null points. So we have to exclude them from our consideration of projective quadrances. So here are the formulas for the projective rotation and reflections, the rhos and the sigmas. We called this star before. A few videos ago, I showed you that in general, rho sub A to B is an isometry. We had a proof of that. That meant that if we take 2 1 points and compute the quadrants between them and then multiply by this symbol, we get 2 more points which have the same quadrants as the original 2 did. And the proof of that was completely algebraic. And if you look back to the proof, you will see that at some point I cancelled an a squared plus b squared from the numerator and denominator. Didn't make a big deal out of it at that time. But whenever you're cancelling something from the numerator and denominator, you should pause and say, do I know that this is actually non-zero? Because if this is 0, then I'm basically getting rid of a problem here, which I really am not allowed to do. Now for the rational numbers, what we were considering before, a squared plus b squared is never 0. Because if we have a proportion, if at least one of them is non-zero, then a squared plus b squared is necessarily non-zero. So that issue does not arise for rational numbers. But for more general fields, it is possible for a squared plus b squared to be equal to 0, and then our proof that this was an isometry, or the corresponding proof that this is an isometry, simply fails. The argument fails. All right, so here's some investigations now that I'm going to leave to you. They're fun, but they do involve a bit of work and becoming familiar with the way things work here in this field with 5 elements. The first is to show that if you take one of these offending fellows, row sub 1 to 2, this is a null point. That if we take any one point and we multiply it by row sub 1, 2, we always get 1 to 2. No matter what we start with here, the endpoint is always 1 to 2. In particular, this thing is not an isometry. And you can also check that the same thing occurs for the sigmas. So when we're talking about isometries, we have to exclude row 1 to 2. And we have to exclude row 1 to minus 2, and also sigma 1 to 2 and sigma 1 to minus 2. So the last exercise is please have a look at what actually this group structure is in the situation of the projective line over F5. So our last exercise, and quite a sizable one, so there's a lot of investigation to do here. I'm going to leave that to you. To investigate the group structure of the isometries of P1 over F5. And our list of isometries notably does not include rho sub 2 or rho sub minus 2 or sigma sub 2 and sigma sub minus 2, because they have this property, well, that they're just not isometries. So it turns out that symbolically at least, the isometries that we have in this situation over F5 look a lot like the ones that we had, in fact look exactly like the ones we had over F3. Show that in fact we get exactly the same dihedral group structure as we did for F3. All right, many interesting questions, I guess, pop up. We've talked about F3 and F5. These are very small finite fields. What happens to bigger finite fields? What kind of multiplicative or group structures do we get when we think about isometries of our simple one-dimensional projective line over these bigger fields? It's quite an interesting question, which we're not quite in a position to tackle yet. We need a little bit more number theory to deal with that. But before I get to the number theory, I'd like to say a little bit more about another extension of this idea of isometries of the projective line. So we're going to enlarge the picture yet more, not just by considering wider possibilities for the fields, but also wider possibilities for the toppings that we're going to put on top of our pizza. Namely, different kinds of metrical structure that we can impose on our projective line. In other words, we're going to move towards relativistic geometry, still in the one-dimensional setting, which turns out to be quite important for relativistic physics. So I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.